Okay, so I think we can start with our second talk today. It's a pleasure to welcome Anne-Laure Dalibard from Sorbonne. Although she can't be with us in person, she's here virtually. And Anne-Laure, thank you very much. So over to you.
Thank you. Well, thank you very much for the invitation. I'm really sorry that I cannot be here. I'm actually quite disappointed, and I hope I'll be able to come later in the trimester. Okay, I also apologize because I'm not really going to talk about turbulence, but I will talk about different kinds of fluid models and with a focus on incompressibility. So it's a subject on which I've been working for a few years with Charlotte Perrin, who's a colleague of mine in Marseille. She initiated me to these problems, which I find very interesting and rich. And so I wanted to share my enthusiasm with you today. So I'll talk about some results on congestion phenomena in fluid dynamics. I'm not sure that all of you are really familiar with such models, so I will start with some physical motivations and explanation of the different models of congestion. And essentially in this talk, I will be studying two different models describing congestion in a, let's say, 1D model, 1D fluid model. One which has a singular pressure and one which is called hard congestion model. And for both models, my purpose will be to investigate the stability of traveling fronts. So this is what I will do in the last two sections. But first, let me tell you a little bit about the underlying modelization. So the goal is to study phenomena in which there are congested zones. So there are several areas of application for such models. For instance, Bertrand Maury, who is a colleague of mine in the ENS, has focused a lot on crowd motion and on the movement of populations. People who have a more, let's say, fluid dynamics background have also tried to modelize multi-phase flows, which is another, let's say, motivation to study such models. And the key point is that you will study fluids in which there are two different zones, a congested one and a non-congested one. In the congested zone, the dynamics will be essentially incompressible, and in the non-congested one, it will be compressible. Okay, and the difficulty is that you need, or the difficulty and the interest, I would say, of such models is that you want to study situations in which both domains are present. So the incompressible zone and the compressible zone will speak to one another and interact with each other. Okay. So first, I will talk a little about how you can modelize such effects and how you can describe the transition between the two zones, the congested one and the non-congested one. So again, I insist, the whole goal is to study situations in which you have the two zones present, because if you have either just a completely congested zone or a completely non-congested one, then it falls within some classical incompressible or compressible model. But here you really want to study both at the same time. So let me first say a few words about what happens, let's say, at a microscopic level. Throughout the talk, I will place myself at a macroscopic description, but it's good to have in mind what a microscopic description could be, just to understand the type of things we're dealing with. And so to study congestion at a microscopic level, you can imagine that you have a system of hard spheres, okay, that cannot overlap. So that means that if each sphere has a radius r, then the distance between two centers needs to be greater than 2r, okay? And to study such models, you have two possible approaches. The first one is to replace spheres by point particles, so forget about the non-overlapping constraint. And but still, you want to avoid or to render in a kind of phenomenological way the fact that you actually have a non-overlapping constraint. And so you're going to add a strong repulsive force in your model, okay? This force doesn't really describe what is going on at the level of, say, molecules or whatever. It's really something that is somewhat artificial, and that is here in order to avoid describing this non-overlapping constraint. Okay. The other possibility is to actually keep the original model and to allow contact between particles. So this means that when particles don't touch each other, let's say they're going to have a kind of they're going to be moved by free transport, and then you're going to need to have another description whenever two particles touch each other. Okay, so this is typically something that was done by Maury and also by Marconnet. So I would say that the first idea falls within a rather classical context, even though it can be difficult to handle if you really have a very singular interaction. But let's say if you work with a given force, then okay, you have some tool, let's say, to do both mathematical analysis or numerical simulation. But the thing that is closest to reality is probably the second possibility. So MD is for molecular dynamics and CD is for contact dynamics. So it's the second option. So the second option is probably closer to what happens in reality. And obviously, in the limits where you have a strong repulsive force, at least formally, the first option should converge towards the second option. Okay. And the other thing that I want to insist on is the fact that when you have okay, so I said that if you have a given repulsive force, then for instance, you might be able to do some numerical simulations, but obviously simulations become harder and harder to do, or more and more consuming, say, when the force gets stronger. Okay. So at the macroscopic level, you have the same type of dichotomy, say, between the different types of models. The equivalent of molecular dynamics, so where you add a strong repulsive force between particles, would be to consider a compressible fluid, so with just one phase, a completely compressible model, but with a singular pressure. Okay, so this is the first model that I will be studying in the rest of the talk, which is an, let's say, 1D Navier-Stokes with a very singular pressure. And this is what is called the soft congestion model. Okay, so it has been studied, for instance, by Bresch, Perrin, Zatorska, and also by Degon and some co-authors. And the equivalent of contact dynamics, where you allow for contact between particles, would be to study actually a diphasic flow. And this is called a hard congestion model. Okay, so here you really have a flow which has one phase which is congested and incompressible, and one phase which is non-congested and compressible. Okay, so again, this has been studied by a number of authors. I'm trying to give some references here, but okay, I'm not claiming that the list is exhaustive in any way. Just to give you an idea of what the strong congestion model look like, I wanted to go back to, I think it's a paper that appeared about 10 years ago by Maury and Audrounef-Chupin and Filippo Sant'Ambrogio. So I won't really be studying this model in the rest of the talk, but it explains, I think it gives a good idea of the type of constraints that we will be dealing with when we talk about congestion. Okay, so you have a fluid with density rho and velocity u, and u depends on rho. Okay, the brackets here indicate that the dependency is not, it's not that u is a simple function of rho. So this is not a conservation law, really. This is really a functional dependency. Okay. And what you want to put into your model are the two following facts. First, rho cannot be larger than 1. Okay, this is typically your congestion. You have a maximal density, which is 1. Okay, and the other thing that you want to input is the fact that you have a target velocity u. This means that when rho is strictly smaller than 1, the velocity small u should be capital U. Okay, this is the equivalent in my when I talked about congestion at microscopic level, this is essentially the same thing as saying that when the particles don't touch each other, they just have a free transport at a given velocity. So formally, what you get is that in the areas where rho is equal to 1, the divergence of u should be positive, or at least non-negative. Why? Because if the divergence were strictly negative, then rho would increase in these zones, and then you would overshoot your constraints. Okay, so formally, this is the type of constraint that you want to have. But obviously, you cannot formulate it in this way because you don't have enough. This doesn't make sense. Okay, because in general, rho would just be an infinity. So the set rho equals 1 is okay, like a Borel set. And so you cannot really enforce that type of constraint on such a set. So what you do is you formulate this constraint, but in a rather dual way. So you introduce a set which I call H1 of rho, which consists of P, which are pressures that have H1 regularity, and which are such that P times 1 minus rho is equal to 0 almost everywhere. So in other words, and then I will also assume that P is non-negative. And so here, this means that P becomes non-zero, and so strictly positive, only in the zones where rho is equal to 1. Okay, so only in the congested zones. And then you introduce a set C-rho, which is the set of functions u in L2, such that u tested against these functions is non-negative for any p, which is in the set H1 of rho, which is positive. Okay, so obviously integrating by parts, you get that the divergence of u times p is always positive, which means which is really the dual formulation of this constraint. Okay, and now so you can check easily that this is a convex set of L2, and so small u would just be the projection onto this convex set of capital U. Okay, so now this u is well defined, and I have a model that, okay, at least formally, should render these two features. And so this is actually a theorem by Maury, Routenef-Chupin, and Sant'Ambrogio. The difficulty to study such a model lies in the fact that you will never have better than L2 regularity. Okay, so you won't be able to apply standard tools in transport equations such as, let's say, Di-Bernal-Lyons theory, generalized later by Ambrosio, and so on. So you cannot even define the characteristics of your equation. But their proof, so there are a lot of underlying convexity assumptions, relies really on the identification of a gradient flow structure and the construction of a scheme using the optimal transport. I won't go too much into that because this is really not what I will be doing in the rest of the talk. But what I really wanted to show you was that kind of structure. Okay, the fact that you have a pressure that only lights up in the congested zones. Okay, this is really the kind of model that I would have. And just the last comment on that model, I asked, so in their paper, they only prove existence because by let's say a compactness method. And so I asked Bertrand Maury if uniqueness had been proved because okay, there's a very large corpus of literature on the subject, and I couldn't quite find if it had been proved, and he seemed to think that I think uniqueness is still open. In their paper, they indicate that they believe in uniqueness, that in such a convex setting, uniqueness should be true. But actually, I think it hasn't been proved. Okay, so now let me introduce the two models that I will be studying here. So the first model will be a 1D compressible model with a singular pressure. So here, U is the velocity of the fluid, and V is the inverse of the density. So it's what's called the specific volume of the fluid. Okay, so my constraint rho or rho epsilon less than 1 will become, throughout the talk, V greater than 1. Okay, and so my singular pressure is epsilon over v minus 1 to the power gamma. So gamma is a fixed power which is greater than 1. Again, this is really a phenomenological pressure. Okay, and the parameter epsilon is very small. So this means that as soon as v is far away from 1, the pressure will be very small. Okay, so again, the pressure only lights up in the congested zones, so when v is close to 1. Okay, and I will endow this model with some far field conditions because I will be studying traveling waves. So I prescribe the value of v epsilon when x goes to plus and minus infinity, and same thing for the velocity. So for a given pressure, this type of model has been studied by Matsumura and Nishihara, for instance, and more recently by Vasseur and Yao. And so I will be studying the stability of traveling waves for that model. And then when epsilon goes to 0, formally at least, what you get is this strong congestion model, or a hard congestion model, which is reminiscent of the one I just showed by Mori and co-authors. So you have a transport equation for the density, which is this one, okay, which is just passing through the limit in this one. And then you have an equation for the velocity, in which you have a pressure pi, which is just the limit of this singular pressure here. And so pi is positive because it's just a limit of a positive quantity, or it's non-negative. And it's strictly positive only in the places where, in the areas where v is equal to 1. Okay, otherwise, when v is strictly greater than 1, the pressure is exactly 0. Okay, so this means that, again, when you have a v which is greater than 1, so the pressure is equal to 0, and you have a kind of compressible dynamics, but with 0 pressure, actually. And when v is equal to 1, then the pressure is present. It's a kind of Lagrange multiplier associated with the congestion constraint, and you have an incompressible dynamic. Okay, so first I will construct some traveling waves for these two models. This is fairly easy, so I will go quickly on this. I'll just show you some features and a picture. And then I will construct some global solutions of the model with a singular pressure in the vicinity of a traveling wave, and both local and global solutions of the congested model, so the hard congested one, in the vicinity of a traveling wave. And so, yes, I should mention here that actually, before our study, I think the well-posedness of this model was open. Okay, I don't think there had been any study of the Cauchy problem for that model. Okay, so now let me say a few words about traveling fronts. So I'll start with the traveling fronts for the limit system, which I wrote here so that you can have it in front of your eyes, because it's the easiest one to study traveling waves. And so I look for solutions that move with a speed s, okay, or with a velocity s. And so I assume that this Gothic U and Gothic V have the following behavior. I assume that they are completely congested on the left half line and completely non-congested, so it's the free zone, in the right half line. So in this, when psi is positive, the pressure is 0 because of the congestion constraint. Okay. So when you look at the first equation, you get a Rankine-Hugoniot condition, quite classically. And then when you work a bit the equation, you find that when psi is positive, V satisfies the logistic equation, so an ODE. And so this is really easy because in that case, we have an explicit solution for this equation. So we know that this Gothic V converges exponentially towards V plus at plus infinity. And the only thing that remains to be done is to identify the value of the pressure here in the congested zone. And this is performed by computing the jump condition. Okay, so you would need, here you have dx of a certain quantity in the second equation. And you don't want that quantity to have a jump, because otherwise you would have a Dirac mass in the equation, which you don't want. So this jump has to be 0, and when you compute the jump, it involves the jump of the pressure and the jump of the derivative of v. And since you know that quantity, the jump of the derivative of v, this will give you the value of p minus. Okay. So here, traveling fronts are easy; they're just flat, and then solution of the logistic equation. Okay. So they're completely explicit. So now let me study the traveling fronts for the model with a singular pressure, which is the soft one. So again, I wrote it here. So you look for solutions that travel at a speed or velocity s epsilon. You plug this into your equation and you get an ODE for this Gothic V epsilon. So you no longer have an explicit profile, but still, since it's an autonomous ODE, you can say a lot of things. So you know, for instance, that there exists a unique solution up to a shift, that it's strictly increasing. These are all consequences of the Cauchy-Lipschitz theorem. And you can also perform both quantitative and qualitative analysis when epsilon goes to 0. So for instance, if you normalize things in a correct way, meaning that you somehow choose the shift in this Gothic V epsilon, then this solution of so the traveling front for the model with a singular pressure will converge towards the traveling front for the limit system. Okay, so everything is nice. And the last remark is that okay, I want my velocity to be bounded, or the speed of my front to be bounded, or to have a finite limit as epsilon goes to 0, and this prescribes the value for my velocity, for my density at when x goes to -infinity. Okay, so essentially the value of v minus should be 1 plus epsilon to the power 1 over gamma. This ensures that p epsilon of v minus is 1, essentially. Okay, for the one. Okay, and so just a picture to show you what happens. So in red, this is the limit profile. So again, you have a constant, completely congested state on the left half line, and then the solution of the logistic equation, which you can recognize here. And here you so Charlotte did this simulation, so you can see two different profiles for different values of epsilon, so 10 to the -2 and 10 to the -3. I think gamma is equal to 2 in these in these simulations. And the last remark that I wanted to make, so I didn't want to put it on the slide because to save a little bit of time, is that when you look at what happens in the transition zone here, actually you can prove that there are small scales of size epsilon to the power 1 over gamma. So what do I mean here? Actually, the velocity always remains bounded. Okay, you have a W1 infinity bound on the say v epsilon. But what you can prove is that actually, but you have a jump of the velocity. And so actually what you prove is that v epsilon behaves like the limit profile here in red, plus some correction of order epsilon 1 over gamma. But the correction is on the scale epsilon to the 1 over gamma as well. Okay, so this will be important in the next section, so that's why I'm mentioning it now. Okay, so now let me talk about the stability of traveling fronts. First for the model with a singular pressure, and then for the congested model. So I'm always considering an initial data, which is a small perturbation of the traveling front I just constructed. And the questions are the following. First, I want to study global solutions. Okay, because the theorems that were proved until then were mostly for local solutions. So we want to have some globality, because eventually what you want to prove is some asymptotic stability. Okay, and to have global solutions, we'll see that so classically, if you use a fixed point argument to construct your solutions, you need to have some smallness somewhere. Okay, and in particular, if you want to construct some global solutions, then I would need my perturbation here to be small enough. And the thing is, the size of the perturbation actually will depend on epsilon, and you need to be quite careful with the admissible size of the perturbation that you allow. So to prove our result, we use I would say a fairly classical scheme. So we perform a fixed point argument for small data, but in a high regularity space. So this scheme is quite classical, but then obviously you need to adapt it to your system, and so you need to figure out the nice properties of the system. So here we use three different tools. First, we introduce a linearized operator that has some nice coercivity properties. So to highlight these coercivity properties, we need to work in weighted L2 spaces. The linearized equation is not stable by differentiation, so we need to also have a commutator estimate for when we apply derivatives to our equation. And then the third tool, obviously, is to have some product laws to control the quadratic terms. So I won't be talking at all about the third tool in this talk, because it's really quite classical, and so it's technical, but it's not very new, I would say. So, but I will be talking about the first two tools to give you an idea of the structure of the system. So to study the stability properties of the system, it's nice to switch to other variables. Okay, so I keep my v epsilon, which is again the inverse of the density, and I change my velocity variable. So I switch to a w epsilon, which is defined in this way, and which is called, I think, the effective flux. It's a variable that was introduced, for instance, by Bresch and Desjardins, what is called now the BD entropy. And so here you can see that when you write the equation in these variables, you have some you exhibit some regularization, let's say, on the density, okay, which was not completely obvious in the previous formulation. Okay, so I will be working with these new variables here. So this w epsilon and the v epsilon. And you need to perform yet again another change of variables. It's better to look at the integrated quantities. So w epsilon will be the primitive of w epsilon minus my profile. And the reason to do that is the following. So you need to look at the structure of your dissipation term here. Okay, when you integrate your equation with respect to x, this dissipation term has the following form here. So it's dx of dx v epsilon, which is my new variable, over a given profile. And here you see that this has a nice structure, because when I'm going to multiply this second equation by capital V epsilon, this term will be coercive. Okay, I won't have any lower order commutator term or anything. Whereas here, if I multiply this by small v epsilon, well, actually I need to remove this Gaussian v epsilon first, and then things are not so nice. Okay, so the reason to switch to these integrated variables is really because of the structure of this dissipation term there. Okay, so that's we really want to have a nice coercivity properties for the linearized system, and these coercivity properties are true for the integrated variables, but not for the original ones. Okay, and so I talked already several times about this linearized operator. So now it's the time to show you what it's like. So here you have a nonlinear quantity. And so when you linearize it, when you say that you assume that this capital V epsilon is small in some suitable Sobolev norm, then this will behave like P epsilon prime of my profile V epsilon times the X capital V epsilon. And same thing here, and linearizing this quantity right there. Okay. So when you look at the equation with the red terms, you will see what the linearized operator looks like. Okay. So the linearized equation is this one. It's really the same one as the. Okay. Here I just get the red terms and remove the nonlinear ones. So this is what my linearized equation looks like. And so you multiply the second equation by G. In that case, you will have a nice dissipation term, which is this one. And you'll have an additional term, which is dxf times G, okay? And then you need to multiply the first equation by minus f over P epsilon of V to cancel out this extra term here, okay? So this weight for f is really to cancel out these two terms. Let's say the cross terms between the two equations. Okay, so when you you multiply this one by minus f over P epsilon and this one by G, and you obtain this weighted L2 estimate. So you have two dissipation terms. So you have one energy which is right there, and two dissipation terms, one involving f and the other one involving dx of G. The remark here is that when you look at the control that you have, the control that you have over G is quite good, okay, because you have no weight in front of G. So here V epsilon is between, say, 1 and 2. So this is essentially a dxg square. So the control that you have over G is quite good, but the control that you have over F is not so good because of these penalizations here and here. Okay, when you look exactly what they are, you see that you have a very good control in the non-congested zones, because in these zones, V epsilon will be far away from 1. And so these two terms, this one and this one, will be like 1 over epsilon. So you get a very good control of F. But when V epsilon is very close to 1, and it can be in the congested zones, these two quantities will be very small, and so your control won't be quite as good. Okay, and so this is really a source of loss in the energy estimate. The fact that you have a poor control in the congested zones is a source of difficulty, and is part of the explanation why we need to have a perturbation that depends on epsilon. Okay, so now, so here I explained, so far I explained this part, okay, tool number 1, what I explained what the weighted L2 energy estimates for the linearized operator look like. And now I need to tell you about this commutator estimate. Okay, so just explain a little how it works. So your system, if you write it in a very abstract way, looks like this. So you have these two integrated quantities, capital W epsilon, capital V epsilon. This is your linearized operator. And when you put all the nonlinear terms in the right-hand side, this will be quadratic. So I won't be talking at all about these quadratic terms. As I said, it's really, you need some product laws, and dealing with it is quite classical, technical, but quite classical, okay? And so in order to work in a space with high regularity, you need to differentiate this with respect to X, okay? And to apply similar estimates to the derivatives. Okay, so you differentiate your equation, but your linearized operator is not stable by differentiation, and so here you will get a commutator. Okay, so you need to have a bound on this commutator. Okay. Okay, so I'm sorry, this slide is not very nice, but so this is the commutator you're looking at. This is the quantity that appears when you perform the the linearized estimates at the next level, okay? And when you look carefully at this expression, you can bound it in 2 ways. This term will be absorbed in the dissipation term. And so because it's, let me show you, it's the analog of this one, rather. And then you have one term, which is like a lower order dissipation term, which was this one, okay? So the term that you had at order 0, but it's penalized with a factor epsilon to the power -2 over gamma. And I think this is, I don't think it's because we weren't precise enough. I think it's really there, okay? So this means that with each derivative, you're going to lose a power 1 over epsilon to the power 1 over gamma, okay? And so the total form of the energy will be a sum of epsilon to the power 2k over gamma times this quantity here. So this one is exactly the one that you have here, except that you have several f is and g will be the successive derivatives of capital W and capital V. And each time you differentiate, you need to add a power epsilon to the power 1 over gamma. Okay, and in practice, you don't need to go too far. You only need to differentiate twice. So in the end, the result that we get is the following. We assume that our initial perturbation has size, so the square of our initial perturbation has size epsilon to the power 5 over gamma. And in that case, the nonlinear system has a unique global solution, and the energy remains of the same size for all times. And furthermore, when the time goes to infinity, you converge towards, okay, so this is a little imprecise, which is the difference between the 2 terms that go to 0. Okay, so again, so you see that the size of the initial perturbation needs to depend on epsilon. This is very stringent, but it's really necessary, we think, because of different things. First, because of the pressure singularity, which explains that you have a very poor control of your solution in the congested zones. And the other reason is the fact that you have small scales in your profile. Okay, and we think that, so this is the remark that I made earlier, you have some small scales that appear in the transition zone, and we think that these small scales are responsible for this loss. Okay, so now I will talk about the other model, the model, I call the hard congestion model, okay? And I would ask the same question. So I wrote again the model here. So it's you have a simple transport. So this is the transport equation. V is the inverse of the density. This is the equation for the momentum. Okay. You have a pressure pi, which is 0 only in the non-congested zone, which is non-zero only in the congested zone. So, okay. And so I already constructed traveling front solutions for this equation. And so if you remember, these traveling front solutions were just completely congested on the left half line and then equal to the logistic profile. Okay, so now I want to perturb a little my traveling front solution and see what happens. So if you have in mind what I just said about the model with a singular pressure, you remember that, so first I needed to have a very small perturbation, and also I had a very bad control of my solution in the congested zones. So here what I'm going to do is take a perturbation that only bears on the non-congested zone. Okay, so I will take initial data which coincide completely with my traveling front solution, so they will be completely flat in the congested zone. Okay, so for psi negative. Okay, so but obviously, okay, I'm still taking some perturbations in the non-congested zone. And so the idea in that case is that you will somehow keep the same structure. So you will remain, if you look at your solution for a later time, it will not be a traveling wave, okay? But you might hope that it will remain congested on a half line and then be completely non-congested, okay? So here I'm plugging in an ansatz, if you want, which is the following. I'm assuming that there exists some x tilde of t, which I don't know, which is such that when x is smaller than x tilde, my solution is completely congested, okay? And when x is bigger than x tilde, then my solution is free, and my pressure is 0, okay? And so I'm looking for solutions that have that type of behavior. And the interesting thing is that the evolution of everything is coupled, obviously, okay? Because the evolution of the solution will impact the dynamics of x tilde. It's a kind of free boundary problem. And also the evolution of x tilde will also impact the dynamics of V and okay, so our result is the following. So I take a perturbation of my profile, but only in R plus C, only in the non-congested zone. I also assume that V naught and U naught satisfy some compatibility conditions, which I'm not writing here. It's because I'm working in a high regularity setting. And then you can prove that there exist local solutions which have the form that I just claimed. So they are completely congested on the half line and then non-congested. And furthermore, if the perturbation is sufficiently small, and here there is no small parameter, okay, it's smaller than some constants that only depend on the parameters of the problem, but there is no epsilon here. So when I say small with respect to 1, it's smaller than a constant that depends on S, mu, and so on. So if the perturbation is sufficiently small, then the solution is global. And in that case, furthermore, it's stable. So the perturbation goes to 0 as time goes to infinity. Okay, so let me give a few some ideas, let's say, about the proof. So first, the first idea is to write the equation. So you still work with the variables W and V. So W is my flux. It's U minus mu log V. And you write it in shifted variables. Okay, so because you want to get rid of your moving boundary, and here it's quite simple because okay, your moving boundary is just a point, so it's easy. So I'm setting psi equals x minus x tilde, and again x tilde here is unknown. And in the domain where psi is positive, I'm assuming that I have that I'm not congested, and so my pressure is 0, and then my equation becomes just this. Okay, so the equation for W is very simple, which means that W is just transported, and it's equal to W naught. It's just a simple transport equation, x plus x t. Okay, and when you plug that into the equation for V, you get the second line. Okay, so you get somehow a closed equation for the inverse of the density Vs. And then you need to understand the coupling between the dynamics of x tilde and the dynamics of V. And to do that, so it's quite similar to what is done, for instance. Okay, so in several papers studying fluid structure interaction, and for instance, recently in the papers by David Lam, Tatsuo Iguchi, and co-authors on floating structures. Okay, they often have that type of condition. So you need to write some jump conditions at the interface. And so the important condition is that V and U need to be continuous. Okay, and so when you write that, you write that V at time t and x tilde of t at point x tilde of t will be equal to 1. And then you differentiate this identity with respect to time. So you will get dtv plus x tilde dxv equals 0. And you use the equation to replace dtv by dxu. Okay, so this is just the continuity of V. Okay. Okay, and then you play a bit with your equations. This part is a bit problem specific, but writing the fact that you have a continuity of your density or velocity or pressure at the interface is really something that is common to all these problems, and this is how you find the dynamics of the interface. And so when you play around with your equations, in the end, you find the type of ODE for x tilde, which is written at the bottom of the slide. It's not really an ODE, it's more of a dynamical system, because here the value of US at time t and at point xi equals 0 will depend on the whole behavior of x tilde between time 0 and time t. Okay, so it's not really an ODE, but yeah, it's a kind of dynamical system. Okay, so this is how you couple the two, the behavior of x tilde to the behavior of the behavior of V. Okay, and so this gives you the strategy to prove the local existence result. It's really a kind of Cauchy-Lipschitz proof. You construct x tilde as the fixed point of a given application, which I called calligraphic A here. Okay, so you assume that you have a y tilde which is given and which is in H2. When y tilde is given, you construct U and V to be the solutions of this first system here. Okay, so when y tilde is given, you can construct V, and once you constructed V, you can construct U. Okay, this is those are linear or non-linear parabolic equations, so it's not too hard. And then once you know about V and U, you can construct Z tilde such that the derivative of Z tilde is given by this. Okay. And when time is not too large, you can prove that you have a fixed point for that you have a contracting application, and then you construct a fixed point. Okay, it's really very similar to Cauchy-Lipschitz. And the core of the proof is to perform some estimates for V and U, and so here you use a lot. So it's really a regularity estimate for parabolic equations. Okay, so this gives you local existence for any initial data. And then the last result that I want to mention is the global existence one. So I won't go into the details of the proof, but there are a few features which I like, and so I wanted to explain them. So now, so you have your local solution at hand, and you hope that this solution is global when the initial perturbation is not too large. Okay. And when I talk about the perturbation, you need to think of the perturbation. So let's say Vs minus this Gothic V, but also x tilde minus S. Okay, everything is coupled. So you really need to consider both things together. Okay, so if this G is not too large, then it's legitimate to linearize your equation around Gothic V. Okay, so this is what you do. You linearize the equation satisfied by G around V. And this is the equation that you get. So here you will get the linearized operator. You have this term which comes from transport. Okay, this comes from the fact so this x tilde. Actually, you have an x tilde prime. Okay, you have an x tilde prime dx vs that comes from the fact that you have a shifted profile, and so you rewrite this as a sum x prime tilde minus s dxv plus x tilde minus s dxg. Okay. So when you write it in this way, you see that the red and the green terms are very different. So the green terms are all quadratic because here g will be small, or you expect it to be small, and x tilde minus s will also be small. Okay, so this is quadratic because again the two are of the same size. Okay, g will control x tilde minus x. And here you will have a log of 1 plus x minus x for x small. So this is again quadratic. So all the green terms will be quadratic, and so you can expect to treat them in a perturbative fashion. The red term, on the other hand, is not quadratic at all. It's a linear term. Okay, so this could be bad. It could be, if you wanted to prove some long time some long time estimates. Okay, but the nice observation, and I think this is in fact quite generic, although I don't recall seeing it mentioned in other occurrences, is that actually what you have here is the derivative of your profile, dxd, and it belongs to the kernel of your linearized operator. This part is really generic. It just comes from the fact that you have an operator which has a constant coefficients. Okay, coefficients that don't depend on space, and so you have a translation invariance, and because of this translation invariance, your the derivative of your profile belongs to the kernel of the linearized operator around that profile. Okay, again, this is really very robust. Okay, and so once you observe this, you can apply your linearized operator to your equation, and the good news now is that the red term disappears. So this G1, which is just the LG, satisfies an equation with this L here, which you hope to be coercive, equals some quadratic terms. Okay, and then it's essentially over, because if you are able to prove that this calligraphic L is coercive, then you will be able to prove a Fujita-Kato-like result for small data, and this is exactly what we do. Okay, and L is a diffusion operator, so if you work in a nice setting, then you'll be able to prove some coercivity properties. Okay, so this is all I wanted to say about the global existence result, but okay, I found this both intriguing, because it seemed to be robust, but at the same time, I don't remember anything which was exactly, I didn't see it formulated in that way in earlier books. So, yeah, I just thought I would mention that. So I'm going to stop soon, but just to give you a summary and some perspectives of that work. So I presented some congestion models, two different ones, one with a singular pressure and one in which the congested was modeled in a hard way, so with a strong constraint. For both models, I constructed some traveling fronts, and can actually describe the transition between congested and non-congested zones. And once these traveling fronts are constructed, you can study their stability. You can do things in a fairly quantitative way within the singular model. So you need to compute to be careful with the size of the initial perturbation and the functional norms in which you compute that size. And concerning the hard congestion model, so I constructed some local solutions starting from any perturbation in the non-congested zone. And then I proved that for small initial perturbations, you actually had some long-time stability. So two questions to conclude. We didn't compute in the second model, in this one. So here I told you you can use some coercivity properties to prove global existence and global stability and so on. I'm fairly confident that actually you can get some type of that you can get a rate of convergence. We didn't do it, but I think you should be able to do it. Okay, so this would be having a kind of spectral gap for L. Of course, you need to be careful because the kernel of L is not empty, because you actually have an explicit profile within it. But probably if you are working in the orthogonal of the kernel, you might be able to prove some spectral gap, and this might be sufficient to to prove, let's say, some exponential convergence. Okay, but we didn't do that. Actually, the main question that we would like to address, and at the moment I don't really know how to tackle that, would be to start from initial data that perturb the profile in the congested zone. So let's say, okay, you in the profile you have all this left half line which is flat, okay, which is completely congested. And you could imagine that to adding a bubble somewhere in this within this congested zone, and understand what the evolution is. So and yeah, at the moment I don't really know how to do that. We started thinking about it a little. It's possible that you have two different free boundaries actually that interact with one another, but okay, at the moment I don't really know how to handle that. Okay, and stop here, and thank you very much for your attention.
Sorry, I didn't have the mic on. Thanks for a very nice talk. So are there any questions in the chat? No, any questions in the room?
Hi, Anne-Laure. Very nice talk. I have two questions. The first one is, so I understand you're interested in traveling front, so naturally you're solving the whole real line. But if people looked at this model in bounded domain and in the bounded domain, and if so, what kind of boundary conditions make sense? That's question number one. Question number two is, so in hydrology, there is a similar issue in the sense that, the pressure becomes, when you have full saturation, the pressure becomes constant. So, but there you typically derive a single scalar equation, which is degenerate. The time derivative vanishes when you reach saturation. So this is like Richard's equation. So I was wondering if people have looked at models for congestion like that. Thank you.
So for your first question, adding some boundary conditions, yes, and okay, I don't think so for instance, in the paper by Mori, which I mentioned in the beginning, it is set in a bounded domain. It's even set in actually a convex domain, and the domain itself is important. So that's a first answer. And but I think in these fluid models, I don't remember them being. I don't remember any reference in a domain, but okay, I don't think it should be a big issue. I think probably you could study that type of problems in domains. Okay, either the compressible one with a singular pressure or the one in which you have two phases. I think you should be able to do that. Of course, you have to be careful which boundary conditions you enforce on the density, because you see when you change the formulation, when you go to the effective flux variable, you have the feeling that you have a kind of diffusion equation for the density or for the inverse of the density actually. And so in that case, you might have the feeling that you can take a boundary condition for the density, which is not really the case if you have transport. So maybe you need to be a bit careful with that. I don't know. Okay, that would be the part that is a bit not completely on solid ground, but otherwise, I don't see why not. And about your second question, I don't think I've heard of that, of modeling of congestion with vanishing time derivative. I don't think so. Not that I am aware of.
Very much.
Yeah, thanks.
No, sorry, I can't hear you.
I don't know if I understood well.
Actually, the mic is going on and off. I'm sorry, I cannot hear you at all.
Can you hear me?
I heard, can you hear me? But that's it. I don't know what the issue is because I could hear Anna fine. Maybe it's a problem of distance to the source, or I don't know.
Anne-Laure, we all have the same problem, so it's not you.
Thank you. Ah, okay. Oh, no problem.
Anne-Laure?
Yes.
Yeah, okay. So, well, he's gonna email you the question. We had a battery issue, you know, with the mics, but thank you so much for the
Sure.
beautiful talk.
Thank you.
Bye-bye.
Yeah, thank you. Thank you. Beautiful talk. And take care, Anne-Laure. Bye-bye.
Thank you. Bye-bye. So I'll stop sharing.
Yes, and you are dismissed for now. You did your part.
Yes, I think.
If you are here, you will be getting free lunch. Believe it or not, there exists such a thing, but sorry about that. Okay. Have a good afternoon. Bye-bye.
Thank you. Bye-bye.
Bye.